In the present video, we will discuss the algorithm of simplex method. While solving any linear programming problem using the simplex algorithm, it is assumed that an initial basic feasible solution exists. Let's see the procedure to determine the optimal solution for simplex method. First step is check whether the objective function of the given linear programming problem is to be maximized or minimized. If it is a minimization problem, then convert it into an equivalent maximization problem by multiplying the objective function by -1. That is, minimization of z equal to minus of maximization of minus z. Let's see the example. Here, objective function is minimize z equal to x1 minus 3x2 plus 2x2. Then we have to convert this minimization problem into maximization problem by multiplying with the -1. Then minimization z will become the maximization z. Then objective function will become the minus x1 plus 3x2 minus 2x2. Let's consider optimal solution for this objective function is the 11. Then maximize z equal to 11 is the optimal solution. Then once again you have to convert this minimization, that is the minimization of z equal to minus 11. Second step is verify that all bi values are positive. Here bi is the right hand side value in the constraint equation. If any bi is negative, then multiply the entire constraint inequality by -1 to ensure that all bi values are the positive. So let's see example. Let's consider the constraint minus 4x1 plus 7x2 plus 5x3 greater than or equal to the -2. Here bi value is the negative. Then we have to multiply with the -1 in the both of the side. Then constraint will become the 4x1 minus 7x2 minus 5x3 greater than or equal to inequality symbol will become the less than or equal to, and -2 become the +2. So here bi value is the positive. And next step is the put the LPP into standard form by converting all inequality constraint into the equation. If any constraint is having the less than or equal to inequality symbol, then you have to add a slack variable. Similarly, if the constraint is having the greater than or equal to inequality symbol, then subtract a surplus variable. And let's see the fourth step. So in this step, we have to determine the initial basic feasible solution, that is xb equal to b inverse b, and place it in the first column of the simplex table and construct the initial simplex table using this basic solution with columns for the basic variables, their values xb, and the coefficient of non-basic variables and the objective row entries. So first we have to construct a initial simplex table. So this is the initial simplex table. So first we have to construct the initial simplex table, and here B is the basic variables. So B is the basis variables. First we have to enter the basis variables. Always in the basis variables it should be the slack variables. And CB is the cost coefficients for these basis variables. Always should be the 0. And XB is the initial basic feasible solution for these basis variables. So here B1 and B2. So and B1, B2 are the right hand side values in the constraint equation, and initially we are considering these values are the solutions. So XB is the initial basic feasible solution for the basis variables, and CJ is the cost coefficients for all the variables, and Aij, that is A11, A12, A13, etc. are the coefficients of the variables in the constraint equation. Let's see the next step. Calculate the net evolutions of Zj minus Cj using the following relation. Zj minus Cj equal to Cb into Aj minus Cj. So after determination of the Zj minus Cj, then we have to observe the symbols of the Zj minus Cj. If all the Zj minus Cj values are the greater than or equal to the 0, then we have to consider the current basic feasible solution, that is XB is the optimal. If at least one Zj minus Cj is the negative, that is the less than 0, then solution is not optimal, and we must proceed to the next step. So let's see the step 6 is the identify the entering variable by key column. So in this step we have to identify the entering variable in the basis, that is the key column. So key column is identifying by observing the Zj minus Cj values. Here we have to select the negative Zj minus Cj value, and its column is the key column, and the corresponding variable is the entering into the basis. If multiple Zj minus Cj values are the negative, then we have to select the most negative value. So let this Zr minus Cr from j equal to the r, the corresponding variable, let consider the Xr, becomes the entering variable and is indicated with an arrow at the bottom of the rth column. After that, so we have to observe the coefficient values in the key column. If all the AIR values are the less than or equal to the 0, then problem is the unbounded solution. If at least one AIR is the positive, then corresponding vector XR enters into the basis. So next step is the determine the leaving variable and identifying the key row. So in this step we have to determine the leaving variable by identification of the key row, and key row is identifying by calculating the ratio of XP divided by AI for the key column, that is the XBI divided by AIR, and here AIR value should be the positive values, that is AIR should be greater than 0. After calculating the XBI divided by AIR, then we have to identifying the smallest value. So let consider this smallest value is the XB k divided by the AKR. Then corresponding variable of this smallest ratio variable is the leaving variable and its row is called as the key row. So after the identification of the key column and the key row, then you have to identify the key element. So key element is the element located at the intersection of the key row and key column. Let's see the next step. In this step, we have to modify the basis variables, that is, form a new basis by removing the leaving variable and introducing the entering variable and updating the corresponding value in the CB column. After that, convert the key element should be the unity by dividing the entire the row by key element. Let's consider here A12 is the key element. Then divide this complete row divided by the A12. So next we have to apply the Gauss elimination method to make the other elements in the key column is the 0, thereby obtaining the updated simplex table. So here we have to change all the elements except the key row by using this formula, that is new element equal to old element minus of product of elements in key row and column divided by key element. So let's see the next step. So in this step, once again I have to go to the step 5 and repeat the procedure until the either an optimal solution is obtained or there is an indication of unbounded solution. So in the step 9, once again I have to observe the conditions of the step 5. So in the step 5, so I have to observe the Zj minus Cj values. All the Zj minus Cj values are the positive. Then current basic feasible solution is the optimal solution. If at least one Zj minus Cj is the negative, then solution is not optimal. Then once again you have to repeat the same procedure until we have to get the optimal solution. So this is the procedure for the simplex algorithm, and thank you.